In this video, we will be discussing solubility, essentially why a solute does or does not dissolve into a solvent. In our discussion of solubility, there are a couple key terms. First, what we're interested essentially is the degree to which a solute will dissolve in a solvent, which is based on the intermolecular forces that hold each of those two components together. Solubility is how much solute can dissolve in a given solvent at a given temperature. If we say something is soluble, that means that the solute will dissolve in the solvent. A common mnemonic device to help you remember whether something will or will not dissolve is like dissolves like. Those components that have similar intermolecular forces are going to be soluble in each other. Insoluble is when a solute will not dissolve in a solvent. We can say things are miscible, and that is where the solute and solvent are mutually soluble in each other. In our discussion of solubility, we're mostly interested in the ability of a solid solute to dissolve in a solvent or a liquid solute dissolving in a solvent. When we're talking about gas phases, all gases are soluble in each other because gases are not being held together via intermolecular forces. When we use the mnemonic like dissolves like, what we are talking about are the intermolecular forces. Intermolecular forces are essentially the interaction between two molecules. When we're looking at intermolecular forces, we're really interested in the strength of the interaction between those two molecules, which is related to the strength of the dipole moments that each can form. The strongest of these interactions are the ion dipole, and the weakest are dispersion, sometimes called London dispersion forces. The dispersion forces, or London dispersion forces, occur through an induced dipole interaction. Essentially what a dipole is it's when you have a plus and minus end to a molecule. So you have a plus charge and a minus charge. For dispersion forces, these are induced dipoles. These occur in non-polar molecules, and what you have is along a bond, because a bond is the sharing of electrons, at some points more of the electrons are on one side of that bond than the other. So you can get a temporary plus end and a temporary minus end. So let's say in heptane, this particular carbon-hydrogen bond, the electrons on that carbon-hydrogen bond are now closer to the carbon than they are to the hydrogen. And again, the electrons are in continuous motion along that bond. So let's say that they are temporarily closer to the carbon than to the hydrogen. That would give you a temporary positive charge near this hydrogen and a temporary negative charge closer to the carbon. The positive charge here will pull the electrons on the neighboring pentane closer towards the hydrogen here, giving it a temporary negative charge. So the temporary positive interacts with the temporary negative, and you get an intermolecular attraction between the two molecules. Because this is dependent on the movement of electrons, it is very temporary. And so what you see is that in these dispersion forces, these induced dipoles come into being and then go away. So they are not permanent, they are not all that strong. On the other hand, you could have dipole-dipole interactions. Dipole-dipole interactions occur when you have two polar molecules interacting with each other. What makes a polar molecule is that you have a plus end and a minus end to the molecule. You have a higher electron density on one end than you do on the other. That higher electron density on one end will interact with a lower electron density on another molecule that has a dipole. So these dipole-dipole interactions occur in molecules that have a dipole, a permanent plus end and a permanent minus end. Because we're talking about permanent plus ends and minus ends, they stay around, they are stronger than the induced dipoles that we saw in the dispersion forces. So dipole-dipole interactions are much stronger than dispersion forces because they are permanent and the dipoles themselves are stronger. A particular example of dipole-dipole interactions are hydrogen bonds. Hydrogen bonds are very, very strong dipole-dipole interactions. They occur when you have a hydrogen atom bound to a nitrogen, oxygen, phosphorus, sulfur, and sometimes chlorine atom. The reason why it's these 5 molecules, nitrogen, oxygen, phosphorus, sulfur, and chlorine, is because these atoms are both small and have a high electronegativity. So they will pull the electrons in the bond closer towards them away from the hydrogen. So you get a very strong dipole on that bond with a plus end near the hydrogen and a minus end near the nitrogen, oxygen, phosphorus, sulfur, and sometimes chlorine. In order to form a hydrogen bond, however, you need both parts of that dipole-dipole interaction to be very strong. So that hydrogen bound to a nitrogen, oxygen, phosphorus, sulfur, or chlorine also needs to interact with a nitrogen, oxygen, phosphorus, sulfur, or chlorine on an adjacent atom. The reason for these molecules, again, are very small and very electronegative. So they will typically have a strong dipole along their own bonds. An example of this would be ethanol interacting with water. These are held together by a hydrogen bond. The last type of bond are ion dipole interactions. Ion dipoles are where you have an ion, something that has only one type of charge, in this case the sodium atom with a plus charge, interacting with molecules that have dipoles. The reason why these are particularly strong are the ions themselves can be thought of as point charges. There is no negative end to this sodium atom. It is a very small, strong, positive charge, and so it interacts very strongly with the negative end of the molecule's dipole for the atom that is polar. So in this case you have water surrounding a sodium atom. These waters, the oxygen is where the negative end of the dipole is. They will be pointing towards the positive sodium atom. Because the ion is a permanent point charge and these dipoles are permanent directional charges, this is a very strong interaction. When we talk about solubility, what we're really talking about is the formation of a solution. When we take two components, a solute and a solvent, and put them together, there is a drive towards mixing. This driving force is known as entropy. Entropy is the movement of things towards a greater state of disorder. If the intermolecular forces are similar in strength between those two components, then mixing will occur. A way of predicting whether two things will form a solution or not is by looking at those intermolecular forces. If the interaction between the solvent and the solute is stronger than the interaction between the solvent and itself, and the intermolecular interactions between the solute and itself, then a solution will generally form. If we have a case where the solvent-solute interaction is approximately the same or equal to the interaction between the solvent and itself and the solute and itself, then again a solution will generally form. We could also have a situation where the solvent-solute interaction is weaker than the solvent interacting with itself and the solute interacting with itself. In this case, a solute may or may not form depending on how big the difference is. This comes into play with the mnemonic, like dissolves like. If we have like types of interactions, such as dipole-dipole or hydrogen bonding interactions in the solvent with itself, the solute with itself, then our solvent and solute will also have those similar types of interactions. But if we have a case where perhaps the solvent is water, which has hydrogen bonding, and the solute is some long hydrocarbon like octane, which is held together by dispersion forces, then an interaction is less likely to occur. A solution is less likely to form. This is where the like dissolves like comes into play. Like forces would be the hydrogen bonding and the dipole interactions between the solvent and itself, solute and itself, and the solvent-solute. But if one set of the forces are much, much weaker than the other, then the solution is less likely to occur because the resulting interaction, a dipole-induced dipole, is weaker than the dipole-dipole interaction of perhaps the solvent.